Good morning, all of you. In this session, we will be understanding a different flavor of pulse code modulation called as differential pulse code modulation. So it is observed that in most cases, the adjacent signals are very similar. So in order to reduce the effective transmission, in order to reduce the bandwidth and so many all the other constraints, we came to understand that it is enough to transmit the difference between the two adjacent pulses so that you are removing out all those that is not required. Okay, all the redundant data, redundant means the things that is being replicated again and again can be eliminated very easily by using differential pulse code modulation, where you are transmitting the difference between the adjacent pulses only. So what happens is that this led to a new form of pulse code modulation, and we call it as differential pulse code modulation. Okay. So this is the block diagram of a DPCM. So here in DPCM, instead of taking the message sample itself, what we are doing is that we are using a linear prediction to the quantized output. Okay. After sampling, we are quantizing the signal, and this quantized version is what is given as an input to the linear predictor. Linear predictor predicts the possible difference in signals. So in this process, what we have the output to be a differential quantizer. Okay, the output is a differential quantized output, and this is being used for transmission. So the advantages, two problems that we will be facing is that waveform encoding in the transmitter requires the use of quantization. Waveform decoding in the receiver has to process the quantized signal. So this is a probable question in your exams. Okay, why do you want to use? What are the two practical considerations? This has appeared in your exam. This is an answer to a university question, so you may need to study that. That's the reason why it is explained here. We need to have two practical considerations. The first one is about the use of quantization, and the second one is that encoding and decoding both will have to process the quantized signals. So let us study the method which is being used to, it is applied for differential pulse code modulation. So the difference EQN is given by EN plus QN, where EN is the difference here, right? You have the sampled version. You have the sampled version of the message signal, MN. You're comparing it with another signal. You have this to a quantizer, and you are having the encoder after this. So this signal is being taken here, adder, linear predictor, and then this is being compared with the sampled version, and only the difference needs to be considered. So this is what we'll get it as DPCM encoded signal. Okay, so QN is the quantization noise produced by the quantizer operating on the prediction error known as EN. Okay, so MQN is given by the output of the predictor. MQN, the input to the predictor, sorry. MQN is given by M plus M tilde plus EQN. EQN is defined here, where QN stands for the quantization noise. So tilde m is a predicted value of the original message using the linear predictor. So according to the theory, we'll get that linear prediction theory, we'll get mqn to be equal to mn plus qn. So now let us study how a DPCM transmitter works. We need to understand the functioning of DPCM, both transmitter and the receiver. So in a DPCM transmitter, you have three important steps. In the first step, the predicted message Mn is compared with the prediction error En, which is quantized. That means that it reduces all the repeated data, only the difference between Mn and tilde Mn, that is the predicted value using a linear predictor, and the En is quantized to form the output of the quantizer. Okay, this is the first step. So in the second step, what happens is that m tilde n, the predicted value, and EQN, okay, the adder in the transmitter produces the quantized version of the original sample message Mn. Okay, then we use this through a linear predictor, and are you listening? Are you able to hear me? Are you able to understand? So you need to mention the three steps at the transmitter. First is that you are predicting a value in comparison with the original one, and you are finding out the difference. The second stage, what you are doing is that the quantized version is further sampled to get the original sample message called as Mn. Okay. The third step, we are passing this through a finite impulse response, FIR predictor, to get the output. This is a multi-stage operation, cyclic, encompassing of three steps that are repeated each time, so that we can reduce. This operation will help us to reduce the message to a great extent. The DPCM code so produced is a lossy compressed version of the sample code, and it is lossy because of its prediction error. You have some error here. Okay. Next, the receiver operation. We have seen DPCM transmitter operation. Now we are going to study the receiver operation. Okay. So what happens in a DPCM receiver is that we are receiving the original, the prediction, this EQN, the error signal that is being received in the receiver, is being reconstructed using a decoder. This is nothing but the quantized version of the prediction error. So an estimate of original sample Mn is then computed by applying the decoder output, because it is the linear predictor that is used in the transmitter is same as that of the receiver. From that, you will be able to calculate, or you will be able to estimate Mn. Okay, so Let us consider that there is no channel noise. In that case, the encoded signal received at the receiver input is same as the encoded signal at the transmitter output. So this is an ideal condition. Under this ideal condition, the corresponding receiver output, that is NQN, differs from the original sample MN only by the quantization error Qn incurred as a result of the quantizing the predictor. Okay. The only difference what we have is Qn. So it is possible for us to reconstruct the original signal. So this is a block diagram of the transmitter and the receiver of a differential pulse code modulation system. We have an analog input signal here that passes through a low pass filter, and then what we are doing is that here is where we are doing the DPCM transmission process. We are generating the DPCM transmitted signal. So as usual, we have a band limited analog signal. Entering here, we have, like for PCM, we have a sampler, quantizer and encoder. Here we are having a linear predictor and we are making a feedback system so that only the difference is being quantized and transmitted. This DPCM sampler, quantizer for any M levels or L levels, and then you have an encoder here. This together forms the DPCM transmission system. Then it is being transmitted through a channel. The receiver's end you will receive a channel noise plus the transmitted signal, DPCM signal. The receiver's end you have a regeneration circuit, decoder, predictor and a reconstruction filter, and then you have the analog output signal. Does this require any more explanation? Is there anybody in the class who did not understand the operation of a differential pulse code modulator? All of you are clear with it? Shall I proceed to the next? WEINER-HOPF equation, extremely important topic and most expected question in your exams. What is WEINER-HOPF equation? Very important. This is the fundamentals for AI, machine learning. So many other ideas have evolved out of WEINER-HOPF equation. The concept of WEINER-HOPF theory is very simple. We have two signals, one after the other. We are going to estimate the other signal without any kind of time delay from the first signal. Okay, this is the basics of prediction theory. It is applicable in many cases. We are going to predict another signal from one signal without any kind of time delay. These are the important characteristics of WEINER-HOPF equation. There is a small correction here. It is not random process, it is random process. So under WEINER-HOPF theory, we have three important considerations. First, we believe that the signal and noise are random processes with spectral characteristics equivalently known through their auto and cross correlation functions. So we have two random processes, the signal and the noise. Okay, we are going to estimate the signal here. What we are doing is a process of estimation. This is a founding theory for so many other hardcore applications. So here what we are going to do is that we are going to use, see, you know what is LSM algorithm, least mean square algorithm? It is deeply used in advanced technologies for both AI and so on, LSTM algorithms and so on. Here we are using an algorithm called as minimum mean square error. Okay, so the criteria for the best performance is the minimum mean square. Okay, this minimum mean square error. This is partially to make the problem mathematically tractable, but it is also a good physical criteria in many applications. In many other applications, we are using this minimum mean square error method to calculate the difference between or the error and predict the next value. Okay, a solution is based on the scalar methods that lead to optimal filter weighing function. These are the characteristics of WEINER equation. So this is the equation here. You have a so here you have a signal Zn, which is Sn plus Vn. Here you are having the predicted signal S tilde n. We have two processes. And the expected thing will be this one S tilde n minus Sn. The expected value of S tilde minus. So this is the definition for WEINER equation. So this is how WEINER equation is derived. The filter input is an additive combination, that is we call it as joint wide sense stationary JWSS with known auto and cross correlation functions. Auto correlation means the relationship of the function with the same function at a different point of time. Cross correlation, you have two different signals. So the output of the WEINER filter is linear and time invariant. You may be asked about the properties of WEINER filters. Okay. The output is compulsorily a WSS process, wide sense stationary process. Do you remember what are the conditions for WSS? A random process to be WSS. The performance criteria is minimum mean square error. So it is reducing the mean square error. We have seen it in the previous equation. So let us mathematically write the convolution process here. The estimated signal Sn will be Hn convolution Zn. In other terms, the summation of all values from I to infinity Hn minus I Zi. Where Zi is the measurement, that means that is it includes the noise signal also. Okay. Hn is the impulse response of the estimator. If H denote the region of support for Hn, then H is defined by n Hn when Hn is equal to 0. So, listen here. We are going to calculate the minimum mean square error. We call it as J. That will be the estimated value of Sn minus Sn tilde. Substituting the values, you will get the mean square error to be we are calculating mean square estimation. See, MSC algorithm is very important for you. This is applicable in many different fields and different domains. So, understanding minimum mean square estimation is extremely important for you, and it is important in different fields including WEINER of equation. This was one among the first methods of predicting values systematically and scientifically. Okay. So the objective is to minimize this value of J. Okay. For that, what we are going to do is that we are going to take the partial derivatives of J with respect to H of J, considering H of J not equal to 0. So to minimize MS, so we are finding out the partial derivative of J with respect to H of I, and we are going to solve it. So here R of K is the autocorrelation function, and RS stands for the cross correlation between the signal and the S. So thank you all. Tomorrow we'll be learning what is delta modulation. Thank you very much.